Hello everyone, welcome to the chemical engineering example number 3. For today, we are going to study how the thermodynamics can affect the catalytic reaction. Just recap, the rule of a catalyst is to accelerate the rate of conversion at the lowest possible temperature. For today, we are going to use the example of SO2 to SO3 conversion in the production of sulfuric acid. For this reaction, it is 1SO2 react with half oxygen to form 1SO3. The enthalpy change of this reaction is negative 98, which means this is an exothermic reaction. This is going to release heat. And in industry, this reaction starts around 400 degrees C, and the catalyst is a vanadium-based catalyst. If this process is operated adiabatically, the heat released during this reaction can raise the process gas temperature to up to 600 degrees C. And we are going to see how this temperature increase is going to affect the SO2 to SO3 conversion. To calculate the conversion, we need to know the equilibrium constant. As shown in this equation 1, this equilibrium constant is a function of SO3 pressure, SO2 pressure, and the oxygen pressure at the equilibrium. And it is also a function of temperature as shown here, equation 2. So for a given temperature, we are able to calculate what is the equilibrium constant. Now let's go to the example. We have a feed gas containing 3.9% SO2, 5.8% oxygen, and we want to calculate how the SO2 conversion changes with temperature. To calculate conversion, we need to know how much SO2 is converted at each temperature. Let's assume that is X. We know at time 0, we have 3.9% SO2, 5.8% oxygen, and we don't have any SO3. If we know the converted amount of SO2 is X, then we know at the equilibrium the amount of SO2 is 3.9% minus X. Oxygen is 5.8% minus half X, and SO3 is X. Now we can rewrite this equation 1, this Kp equilibrium constant, as a function of the converted amount of X. So this is going to be our equation 3. And for this equation 3, we can simply just rearrange it into this equation 4. So as we mentioned earlier, we can combine this equation 4 and equation 2 to calculate the converted amount of SO2 at each temperature. So here we are going to study 5 different temperatures like 350 up to 550 degrees C. And at each temperature, we can use this equation 2 to calculate what is the equilibrium constant. After we calculate this equilibrium constant, we know this Kp in this equation 4. We can then calculate at each temperature what is the converted amount of X. And for this equation 4, it will be difficult to calculate manually, so we are going to use a function called fsolve in Python. So now let's go to the Python program. Here you can see we are starting at 350 degrees C all the way up to 600 degrees C, but not included 600. The temperature difference between each set point is 50 degrees C. Once we have the temperature input, we can calculate the equilibrium constant for each given temperature. Once we know the equilibrium constant, we can use this fsolve function to calculate the converted amount of X at a given temperature, and the result is shown here. As you can see, at 350 degrees C, we have the converted amount of SO2 is close to 3.9%, which means we have a very high conversion. When the temperature is up to 550 degrees C, the converted amount of SO2 is about 3.2%. So we can see as the temperature goes up, the SO2 to SO3 conversion decreased. Now if we plot the conversion with temperature change, we can see the trend more clearly. So here is the SO2 conversion change with temperature. As we can see here, at 350 degrees C, we have almost 100% conversion. At 400 degrees C, we have roughly like 98% conversion. As the chemical reaction happens, the process gas temperature can be heated up. When the temperature is heated up to 550 degrees C, the conversion dropped from almost 100% down to around 80%. In industry, for the sulfuric acid production, in order to improve the SO2 to SO3 conversion, multiple heat exchanger is applied in order to maintain the process gas temperature at a certain window. I hope this is a good example to show how the thermodynamics can affect the conversion of a catalytic reaction. Thank you for watching. Bye bye.